1 minute, sir.
Okay, till that I think Leah, can you do that? Leah. Yes, Leah is there.
Merit factor, sir.
Yeah.
Merit factor.
Huh? Yes, what Manish, what we have discussed yesterday?
Merit factor, sir.
Huh? Can you repeat, man? Hello.
Figure of merit, sir.
Figure of merit. Yeah, now it is very clear. So we have derived the expression for figure of merit for what type of receivers? Okay, what are the different receivers? Yesterday we have discussed and we found what is the value of figure of merit for those receivers. So no idea. Yes, what about Leah? Leah.
Mm.
Yeah, can you just brief about the previous class discussion? Leah? Yes, Ananta. Ananta.
Sir,
ಹೇಳ ಏನ್ ಹೇಳ
sir, we discussed figure of merit. We took different ratios where it was equal to one
figure
for
of merit
different
of
cases.
which receiver we have discussed.
Cases where it was equal to one.
Oh, okay, is equal to 1 for which receiver, man? The figure of merit will be equal to 1 for which receiver? Is it DSBSC receiver or AM receiver?
DSBSC receiver, sir.
DSBSC receiver, right? So what is the value of figure of merit for AM receiver when the message signal is a sinusoidal signal? How much we found it is?
K square P by 1 plus K square P, sir.
Yeah, that is in general. Okay, I told the message signal is a sinusoidal signal. So if it is a sinusoidal signal, so what will be its average power? We denote it by P, no? Which is equal to, means if I take the sinusoidal message signal as m of t, which is equal to am cosine of 2 pi fmt. So its average power will be what? A squared m by 2. Right? If you substitute P as A squared m by 2 in that expression, what do we get?
Half K square A square M by 1 plus half K square A square M.
Yeah. So we know that K squared A squared M, it is means Ka into AM is nothing but mu. Right? That is a modulation index. So we have replaced that K squared A, then K squared A into A squared M by mu, right? So we can write the figure of merit for the AM receiver as mu squared divided by 2 plus mu squared. Is it so? Yes or no?
Yes, sir.
So what is that mu? Mu is a modulation index, right? So when there is 100% modulation, then we get the figure of merit as how much?
1 by 3.
Substitute mu as 1. So we get a figure of merit as how much?
1/3, sir.
1/3. So which is less than?
1.
Less than 1. So we say that the performance of the AM receiver, right, using envelope detector in the presence of noise is inferior to the performance of the receiver of DSBAC in the presence of noise. Isn't it? Because for DSBAC receiver, we found that the figure of merit is 1, right? But for AM receiver, the figure of merit was less than 1. Okay. So I hope till that we have discussed it. Yes, I hope you will be able to see this expression also. I kept for just a revision. Okay, so this is what I was asking about you people. Fine. Then I was discussed about the threshold effect, right? So what it is? Threshold effect means, yes, anyone can say what it is? I said when the carrier to noise ratio is small compared with unity. Okay, this carrier to noise ratio is small, right, compared with unity. Then what happens? The noise will be dominating the uh, noise term will dominate with the expression what we have got, right? So with that, what we can say is the performance of the envelope detector changes, right, completely. Okay, so with that, what we can say is we can express this narrowband noise in terms of its envelope and phase like this. So n of t will be equal to r of t is the envelope and cosine of 2 pi of ct plus psi of t. Here psi of t is the phase, right? So we can write r of t as square root of that in phase component plus quadrature component, and psi of t is the tan inverse of in phase component and quadrature component. I said this is the expression what we get for output, right? And here I said the output of the envelope detector proportional to, it is not directly proportional to the message signal because uh, see, there is no message component only in this term and in this term. Only in the third term I have a message component which is also multiplied with this noise phase, right? So what I wanted to say is here, so with this, right, with this, when the carrier to noise ratio is very low, right, the detector output will not have any component which is directly proportional to the message signal. Okay, that's what the meaning is. So as I said in the last term, only the message signal is multiplied by what? The noise, right, in the form of cos psi of t. So uh, what I would like to say is here we have a complete loss of information, okay, in the detector output. So that does not contain the message signal at all, right? So this loss of message in an envelope detector that operates at very low carrier to noise ratio. Okay, that we call it as a threshold effect. Okay, so threshold here, the value or the meaning of threshold is a value of the carrier to noise ratio below which the noise performance of a detector deteriorates, okay, deteriorates much more rapidly than proportional to the carrier to noise ratio. Okay, so that is the meaning of threshold. Okay, so threshold means what? A value of the carrier to noise ratio below which the noise performance of the detector deteriorates, okay, much more rapidly than proportionately to the carrier to noise ratio. This is how we define the threshold effect. Okay, and this threshold effect will be there whenever we use the non-linear devices or non-linear detector in the receivers. Okay, for coherent detectors, this the effect of the threshold will not be there. Okay, so we don't find such effect in the coherent detector. Okay, because in the coherent detector we don't use the non-linear device. Fine. Okay, so today we'll discuss about the noise in FM receivers. Okay, so in the previous class we have discussed the noise, the effect of noise, okay, in the DSBC receiver and as well as AM receiver. we found that see, how do we measure the performance of the receiver? By finding the figure of merit, right? So for finding the figure of merit, we need to find the output SNR and as well as the channel signal to noise ratio. So the ratio of those two will give you the figure of merit. So that will be indicating how the receiver performs in the presence of noise, right? So similar to that, let us have a discussion about the FM receiver, how noise performs in the FM receiver. So this is the receiver block diagram. So as usual, the input to the receiver will be the frequency modulated signal S of t. Then there will be a white noise, right? So we say W of t. Then output of that will be given to the band pass filter. Okay. So this X of t will have the sum of the modulated signal and as well as the filter noise. So here we write S X of t is equal to S of t plus N of t. So S of t is the frequency modulated signal now, and N of t is the filtered noise. So that is a narrowband noise we say. Then, so this part is all related to the detector circuit, right? So we have a limiter here. We have a limiter. Then that is given to the discriminator. So discriminator is the what? Detector circuit, right? This is a detector circuit. Then output of the discriminator will be given to the low pass filter. So output of the low pass filter will be our demodulated signal. That is the original message signal, right? So let us see, try to understand what is the purpose of this limiter. So why do we use the limiter here? And what discriminator? Already you know what is the discriminator, how does it demodulate the signal, right? And why do we use the low pass filter? So to begin with, so we consider this white noise, right, which is adding at the channel, no? So that will be modeled as the white Gaussian noise, okay, having a zero mean, okay, its value mean is 0 and the power spectral density will be n0 by 2. So this is a standard assumption which we are doing it for all type of receivers, okay. So by assuming this is a white Gaussian noise having 0 mean and power spectral density of n0 by 2, we'll be able to simplify many mathematical computations. So this I told in the beginning only, right? So after understanding this, then so the received FM signal, right? Okay, the received this FM signal will have a carrier frequency, right, which is denoted by FC, and the transmission bandwidth of BT, right? So we know if it is a narrowband FM, what will be its spectrum and what will be its bandwidth and all, right? So that is what is told here. So this will have a negligible amount of power lies outside the frequency band of this FC plus or minus BT by 2. Okay, so for positive frequencies, fine. Then see output of the band pass filter, right? So we need to think about what is a band pass filter. So we think that the band pass filter has a midband frequency FC, right, and a bandwidth BT, and this will the band pass filter will be able to pass that FM signal, okay, without any distortion because its midband frequency and bandwidth is sufficient to pass the modulated signal. Okay, so since this bandwidth of the band pass filter is small compared to the midband frequency FC, then we can represent the narrow band representation of noise in terms of in phase and quadrature phase components. Okay, so that also we have discussed. Then, as we know that in case of FM, right, the message information is transmitted by the variations of the instantaneous frequency of the carrier wave, right? Means the information resides on the frequency of the carrier in case of frequency modulation, and the amplitude of the carrier will be maintained constant, right? So because of this, if any variations in the amplitude of the carrier signal at the receiver input, that will be due to the noise, okay, or we say that is due to the interference, okay. Is this fine? Hello? Hello?
Yes, sir.
Yeah, thank you. So just I'm briefing about the each and every block of the receiver, right? Yes. Okay, then let us discuss the importance of limiter, right? Output of the band pass filter will be given to the limiter now. So what is the function of that limiter? So we call that as an amplitude limiter, right? So what it will do is it will remove the amplitude variations. Okay, if there is any amplitude variations in the received signal, that will be removed by this limiter. Okay, how does it will remove the amplitude variations? By doing the clipping operation. Okay, it does the clipping. Okay, I hope you have studied the clipper circuits, right? So clippers are nothing but the limiters, amplitude limiters. So that is how you should be able to apply that knowledge here. Okay, so because in case of FM, as I said, the amplitude of the frequency of the modulated signal should be constant. Okay, only there will be a variations in the frequency of the carrier signal. Means information is carried in the frequency of the carrier, right? So if any variations in the amplitude of the received FM signal means that is due to noise or interference. So that has to be removed. Okay, to do that we use the amplitude limiter at the receiver side. Okay, after band pass filter we use the limiter to remove the amplitude variations. Okay, so by clipping the modulated signal, right? Fine. Then, so if I do that, I will be getting the rectangular waveform, isn't it? If any variations in the amplitude of the frequency modulated signals are there, if I remove that, I will be getting the pure rectangular waveform, right? So that will be rounded off by another band pass filter. Means that limiter circuit will also have one more band pass filter. So it is which is an integral part of the limiter circuit. Okay, so limiter will be removing the amplitude variations of the frequency modulated signal by doing the clipping operation. Okay, along with that it will also have a band pass filter, right? So that will be suppressing the harmonics. See, square wave we are getting means is what? It will have a number of harmonics, right? So when does it will be having a band pass filter, so it will be removing or suppressing the harmonics of the carrier frequency. So when it is suppressing the harmonics, then we can expect that the output of the limiter, so which is nothing but I said that the limiter will have clipper circuit followed by a band pass filter. So output of that will be again a sinusoidal signal. Okay, output of that limiter will be again a sinusoidal signal. So with an amplitude that is independent. Okay, that amplitude is independent of the carrier amplitude at the receiver input. Okay, because at the receiver input, the amplitude of the carrier may be varied because of the noise, okay, or due to the interference. Now, after passing it through a limiter block, so what it will do, it will remove that amplitude variations, and as well as it as also a band pass filter that will suppress the harmonics. With that, I will be getting a pure sinusoidal signal, right? And the amplitude of that sinusoidal signal will be independent of the carrier amplitude at the receiver input. Fine. So that is all about the limiter circuit. I hope you understood the importance of limiter. Okay. Yes, I discussed it about uh, two components as of now. I discussed what is this band pass filter, what is the limiter. Okay. Next discuss about the discriminator. So anyone can say what the discriminator circuit will have. Discriminator. Yes, I expect somebody to answer this. Discriminator. Of course, I have not thought about limiter. That is why I told about the limiter, what it will do, and it consists of what. But already I have discussed about the frequency discriminator, right? So it consists of what? Quickly, anyone can say. Frequency discriminator circuit. And even we have discussed the two types of discriminator circuits. One is a simple discriminator, and another one is the balanced discriminator. Yes, I expect the answer from you people. Yes, Manish, can you say? Manish? No. Manjunath?
Sir,
Can you tell about the discriminator man? What the discriminator circuit will have?
Sir, sir, ಅದು input like input will be changing. Frequency modulation will be there after when it is passed through discriminator, it will be amplitude modulating, sir.
Fine, fine. What you are saying is exactly correct. But is it possible to say in terms of circuits? So which circuit will convert that variations in the frequency into variations in the amplitudes? See, it
Sir,
will.
is it tuning circuit?
Yeah, very good. So it will have a tuned network, right? Right?
Yes, sir.
Then followed by an envelope detector. Okay, good, fine. Yeah, just let me say about that discriminator, right? So the discriminator will have the two components. Okay, so what are those two components? One is the slope network, right? Or this slope network is also known as the differentiator. Okay, slope network is also known as the differentiator. So what it will do? So it produces the hybrid modulated signal, right? That is both amplitude and frequency will vary. Yes or no? Okay, so that will vary in accordance with the message signal, what I can say. So that is what is the first component of the discriminator. Then second component will be what? The envelope detector, right? The slope circuit or the differentiator will do the what hybrid modulation. Means it will have both amplitude and as well as frequency variation in accordance with the message signal. And second component is the what? Envelope detector. So what this envelope detector will do? It will recover the amplitude variations and reproduces the message signal. Okay, so that is how we say the discriminator is a frequency demodulator, right? So it has a slope network. That slope network is also known as, I said, differentiator. Okay, so that will produce the hybrid modulated wave, means it has both amplitude and frequency variation. The second component of the frequency discriminator is the envelope detector that will recover the amplitude variations and produces the message signal. Okay, so both this slope network and as well as the envelope detector will be integrated and as integral part of the single physical unit. So in a nutshell, we say just discriminator. Okay, the discriminator circuit will have these two components. What are those two? One is the slope network or differentiator, we say. The second component is the envelope detector. Okay, so after the discriminator, if you go back to that block diagram, yeah. Yes, after discriminator, we are using a low pass filter, right? See, output of this discriminator is given to the low pass filter, right? Then output of the low pass filter will be the desired demodulated signal, right? So what is the function of that low pass filter? Let us see. So we have discussed it about limiter, we have discussed it about the discriminator. Then, so that filter is known as the post detection filter. Okay. So we call it as a baseband low pass filter, and that filter will be having a bandwidth, okay, that is large enough to accommodate the highest frequency component of the message signal. Means its bandwidth is limited to the highest frequency component of the message signal. So this filter, that is baseband low pass filter, will remove the out of band component of the noise, right, which is present at the discriminator output. You will understand this with mathematical expressions. So what I am saying is this filter will remove the, means the baseband low pass filter, which is connected at the after the discriminator will remove what? The out of band component of the noise which is present at the discriminator output. Okay, so with that it will keep the effect of output noise to the minimum value. Okay, so that is the purpose of using a baseband low pass filter at the output of discriminator. Okay, so means it will remove the out of band noise component, right? So with that it will be minimizing the effect of output noise to the minimum value. With that, we say the performance of FM receiver is superior compared to any other AM receivers, either uh, DSVC receiver or even the AM receivers. Okay, fine. So far I didn't discuss anything about the mathematical equations, right? Just I told in brief what is what, the function of each and every block, right? Starting with what is the input to the receiver. I said it is a frequency modulated signal, right? Another input is what? White noise. Then that will be passed through a band pass filter. So output of the band pass filter is what? We get the frequency modulated signal plus the filtered noise. I said the filtered noise will be represented in terms of in phase and quarter phase components, as we all know that. Then output of the band pass filter will be given to the limiter, that is amplitude limiter. So that purpose of that limiter is to remove any amplitude variations in the frequency modulated signal. Okay, that amplitude variations may be due to the presence of noise or may be due to the interference. So that will remove, means limiter will remove the amplitude variations of the frequency modulated signal by using or by clipping of the frequency modulated signal. Okay, and then that limiter will also have a band pass filter as an integral part of that. So that will be removing the or suppressing the harmonics. Okay, so we get a pure square wave. Then if any, because of that band pass filter which is going to remove the or suppressing the harmonics, we get a sinusoidal component as output of the limiter, right? So that will be given as input to the discriminator. As I said, the discriminator will have two components. One is the slope network, and it is also known as the differentiator. So basically, differentiator is a high pass filter. Okay, so that will provide an hybrid modulated signal, which is varying both in amplitude and frequency in accordance with the message signal. Okay, so the envelope detector will recover the amplitude variations, and we say it reproduces the message signal. Okay, so both slope network and as well as envelope detector will be implemented as an integral part of the single physical unit. Then output of the discriminator will be given to the baseband low pass filter. Okay, so the baseband low pass filter will have a bandwidth which is large enough to accommodate the highest frequency of the message signal. Okay, so that filter will remove the out of band component of the noise which is there at the output of the discriminator. Okay, so with that, it will keep the effect of noise, okay, output of effect of output noise to a minimum level. Okay, so with that we say the performance of FM receiver is superior compared to any other AM receivers. So now let us try to express in terms of mathematical equations. So as I was telling, the filtered noise, that is output of the band pass filter, right? So it is N of T we represent, right? And since it is a band pass filter, right? And we can define this filtered noise in terms of in phase and quadrature components. This already we have discussed in the previous two classes only, right? So N of T can be expressed as Ni of T cosine of 2 pi fct minus Nq of T sine of 2 pi fct, right? So something into cos is the in phase component, something into sine is nothing but the quadrature component. Fine. So I express the filter noise in terms of in phase and quadrature phase component. Okay. And I said this can also be expressed in terms of envelope and phase, right? So this is one way of expressing the filter noise. One is in terms of in phase and quadrature phase component. The second one is we can express the filter noise in terms of envelope and the phase. So this also we have discussed, right? So I can express in terms of envelope and phase as like this. So N of T will be equal to R of T. So this is the envelope, R of T. Then cosine of 2 pi fct plus psi of t, where psi of t is the phase. Okay. This is the second one. So where this R of T will be equal to what? You can write it as square root of N square I of T plus N square Q of T. So this is the envelope. We define envelope like this. Then, and we define the phase as tan inverse of NQ of T by NI of T. Okay, just I'm repeating, I think I have told this in the previous class also. How do we represent the filtered noise in terms of in phase and quadrature phase component and as well as envelope and phase? Okay, so here we consider this envelope R of T is the Rayleigh distributed. I hope you are all aware what is this Rayleigh distributed PDF, like Gaussian probability density function, or even uniform distribution. Like similar to that, there will be a Rayleigh distributed function. Okay, so we think, or we consider the envelope R of t is Rayleigh distributed, and phase, okay, psi of t is uniformly distributed. Okay, so please keep this in mind. The envelope will be Rayleigh distributed. So the Rayleigh distribution will be like this. It looks like this. Okay. It will be like this. Okay. So Gaussian will be at the middle. So this will be at one end. Okay. So I hope this is clear, this point. Just I am discussing here, how do I represent the filter noise in terms of in-phase component and quadrature component is one way, and other way is in terms of envelope and phase. Okay. Then let us consider now the FM signal, right? So we also know how do we represent FM signal mathematically, right? So S of t will be equal to AC cosine of 2 pi f ct plus 2 pi k of integral 0 to t m of tau into d tau. So this is one way of expressing the frequency modulated signal, right? And we say AC is the amplitude of the carrier, right? And FC is the frequency of the carrier. That's what is told here. AC is the amplitude of the carrier, and FC is the carrier frequency. What is this KF? Similar to Ka in AM, we say here KF is the frequency sensitivity. Okay, and this M of t is the message signal, right? So I can express this 2 pi kf, okay, 2 pi kf integral 0 to t m of tau to d tau as pi of t. To just put it in a simple manner, okay. So I can treat this 2 pi kf integral 0 to t m of tau to d tau as pi of tau, pi of t. Then I can rewrite this expression for FM signal as S of t is equal to AC, right, cosine of 2 pi fct plus pi of t. Okay. So any doubt in this? Just we are expressing the FM signal, and this already we have discussed many times. Yes, do you have any questions so far to ask? Yes, I will ask you people to say the equation, okay? If you don't respond, then I will not give attendance. Okay, fine. I will go to the next slide, then I will ask. Fine. So far, I hope just I said how do we represent the frequency modulated signal? Then how do we represent the filtered noise? So now I am writing the output of the band pass filter. Okay. So output of the band pass filter is what? X of t, which is equal to what I said, the frequency modulated signal, right? The frequency modulated signal, that is S of t, and the narrowband noise, or filtered noise we say, right? So just I'm substituting the value of S of t and as well as N of t. So I think, yes, here I have, yeah, this is my S of t, okay? That is AC cosine of 2 pi fct plus pi of t. And this one is what? My N of t. I'm writing here N of t in terms of its envelope and phase. Okay? So this is the output of the band pass filter. So now let us try to understand this. Means how do we draw the phasor diagram? Okay, so from the phasor diagram we'll be able to define what is theta of t. Okay, so it is informative to represent this output of the band pass filter by means of phasor diagram. Okay, I will show that phasor diagram and we'll come back and see how do we get this equation. Okay, fine. So here I am taking in the phasor diagram. Okay, so I am using this signal term. Signal term means this S of t, right, as the reference. Signal term as the reference, right, and phase theta of t of the resultant phasor representing the X of t. I will show first the phasor diagram. Okay, so this is the phasor diagram. What I can write by considering high carrier to noise ratio. Okay, so only by considering the carrier to noise ratio is high, we are doing this. Okay, all these analysis. So this is my signal, okay, right? And this angle is what? Theta of t minus phi of t. And this angle, okay, this angle, whatever is written here, that will be psi of t minus phi of t. Okay, so this is my r of t, that is what? Envelope. Okay, r of t is this component. Okay, r of t will be equal to what? I can write square root of n square I of t plus n square q of t, right? So if you project this, to this axis, let me write with solid line only. Okay, and this will be what? My quadrature component. Sorry, I think. Yeah. And from year to year, okay, from year to year, I can please have a note of this. Okay, so by projecting this, we can write based on that diagram. Yes, please have a note of that. So I can write this term. So this is R of t, right? And this will be, I think I will tell with respect to that. Yeah, this horizontal axis, okay, this whatever the flower I have done, this I can write it as R of t cosine of psi of t minus phi of t. Okay, this component will be what? I will highlight with red. Okay, this will be what? From year to year, it will be R of t cosine of this angle, psi of t minus phi of t. And this one vertical, this one will be what? This will be R of t into sine of this angle, that is psi of t minus phi of t. I hope you understood. Yes, this will be what? R of t, this component will be R of t into sine of this angle. Okay, psi of t minus phi of t. And horizontal, this point will be R of t into cosine of this angle, R of t minus psi of t. Okay, so here what is written? Theta of t, right? So theta of t, how do I get the theta of t? So this angle, right? So this angle will be what? Theta of t minus phi of t. Okay, so from this I am writing the expression for r of theta of t. Okay, so theta of t will be equal to, so this is theta of t will be equal to pi of t plus tan inverse of, see, that is quadrature component divided by the in phase component, right? So r of t sine of psi of t minus pi of t divided by AC plus this one r of t cosine of psi of t minus pi of t. Okay, is this clear? What I am asking? How do I write this theta of t? Yeah, this is the component AC, right? From year to year, the signal component AC carrier, right? From year to year, as I said, it will be R of t into cosine of this angle. Okay, psi of t minus pi of t. And this vertical one is what? R of t into sine of this angle, psi of t minus pi of t. So to write the expression for theta of t, okay, so theta of t will be equal to this psi of pi of t plus tan inverse of this one, r of t into sine of psi of t minus pi of t divided by AC plus r of t cos of psi of t minus pi of t. Okay, so we are interested in the envelope variations at the band pass output. Okay, see, the envelope of the x of t is of no interest, because why I am writing only for angle is I am interested in phase variations, not in the envelope variations, because the envelope variations will be removed by the limiter, right? So a limiter is going to eliminate that variations in the envelope of the signal, right? So our aim is to determine, right? Our aim is, our motivation, what we can say, is to determine the error in the instantaneous frequency of the carrier wave, right? That is caused by the presence of filter noise. So this is what we are interested in, not in the envelope, because we are using the limiter to remove the variations in the amplitude of the signal. Okay, so with that, as I was saying, we are interested in determining the error right, in the instantaneous frequency of the carrier wave caused by the presence of the filtered noise. So with that, we assume the discriminator is ideal and its output is proportional to this theta dash of t by 2 pi, where theta dash of t is the derivative of theta of t. Okay, so as I said, the discriminator will have a slope network. The slope network is also known as a differentiator, right? So obviously I can write the output of the discriminator will be the derivative of d by dt of theta of t. That is why I write here theta dash of t, okay, over the interval 2 pi. Okay, so with this, this equation seems to be complex, okay, but we simplify this by doing the approximations. Let us try to understand what are those approximations we do to simplify that. Okay, so we are assuming the carrier to noise ratio will be measured at the discriminator input and which is large compared to the unity. Okay, the carrier to noise ratio will be measured at the input of the discriminator and which is large compared to unity. Okay, and if I take R as a random variable, right, which is obtained by the envelope process with sample function R of t, okay, then I say the signal component, that is the carrier amplitude AC, will be much greater than this R of t. Okay, right, that is why we simplify that expression theta of t, that is phase, okay, in the previous equation as pi of t plus R of t into sine of psi of t minus pi of t divided by AC. So I am neglecting this cosine function, whatever I am saying here, right? So this part, because this AC, this component will be much greater than this component, okay, R of t. That is why I can neglect this. And I can approximate as theta of t as what? Pi of t plus that. Okay. Hope this is clear. So I can write theta of t as pi of t plus R of t by AC into sine of psi of t minus pi of t. Yes, is this approximation is clear?
Yes, sir.
Then, then we know what is pi of t, right? Pi of t I have defined, which is what? 2 pi k of integral 0 to t m of t into dt. Just I am substituting here. Okay, theta of t will be that plus the remaining term R of t by AC sine of psi of t minus pi of t. Just I substitute the value of phi of t in this equation. Okay, nothing done is here. Then, so what will be the output of the discriminator? I denoted the output of the discriminator as V of t, right? So which is equal to, so I said what it is having a differentiator, right? That is a slope network. So I can write V of t is equal to 1 by 2 pi d by dt of theta of t. Okay, that 1 by 2 pi is the interval. Fine. So means I am doing the, that is what I get at the output of the discriminator as the derivative of this. Okay, so V of t will be equal to that. So if you do this derivation, what you will get? If you take the differentiation of this, so 2 pi will get cancelled, right? So kf into m of t as the first term will get, right? Then this term, that is a differentiation of d by dt of entire thing, will be denoted as nd of t. Okay, there is a noise component, okay, which is appearing at the output of the discriminator. Is this fine? So I am defining what is nd of t. So nd of t will be equal to 1 by 2 pi AC, right? And then d by dt of this component, R of t sine of psi of t minus pi of t. Yes, is this clear? Or do you have any doubts? So though it looks complex, but it is nothing. It is very simple. Yes, is this clear? The output of the discriminator will be what? 1 by 2 pi d by dt of theta of t. So what is theta of t? I have written, right? So just if I do the differentiation of this equation, what I get? Kf into m of t as the first term, right? The 2 pi will get cancelled. Then the second term, I am denoting it as nd of t. That is to represent, this is the output noise at the discriminator output. Okay, this is a noise component at the discriminator output. So where I defined nd of t as this 1 by 2 pi AC d by dt of this one R of t into sine of psi of t minus phi of t. Okay. Now see, then this component will be passed through a low pass filter, right? That is baseband low pass filter, right? So this is the output of the discriminator. Fine. So it what I observe from this is, so it has a message component, right? And plus noise. So they are additive in nature. So this we used to discuss and discuss it in the DSBC also, right? Yes or no? Yeah, I think same thing. I am repeating it here. Here, see what I said is the carrier to noise ratio will be high, right? So the discriminator output will be consisting of what? Original message or modulating signal M of t multiplied by that constant factor kf plus the additive noise. Whatever is written in the equation form, it is written here in the words, right? So we can use that for finding the output SNR, output signal to noise ratio. Okay, is that fine? Yeah. So now, yeah, he is telling us something about this output of the discriminator noise component. So that will be written as 1 by 2 pi AC d by dt of r of t into sine of psi of t. So pi of t is eliminated. Why we are neglecting pi of t is, so here combination of the signal term pi of t, no? So we know that the phase psi of t is uniformly distributed, right, over the interval 2 pi radians. Okay, so we assume that the phase difference, this psi of t minus phi of t, is also uniformly distributed over the interval 2 pi radians. Okay, so with that assumption, okay, so we can think that the noise at the discriminator output will be independent of the modulating signal. Okay, and it depends only on the characteristics of the carrier and as well as the narrowband noise. I think this is an important point. What we would like to note is the phase difference psi of t minus phi of t is also uniformly distributed over the interval 2 pi radians, right? With that assumption, what I am saying is the narrow noise, okay, which is appearing at the output of the discriminator is also independent of what? The modulating signal, okay, and depends only on the what? Characteristics of the carrier and as well as the narrowband noise. Okay, so with that assumption, okay, what we can write that is justifiable with the high carrier to noise ratio also, and we can simplify the expression for noise component at the output of the discriminator as this 1 by 2 pi AC d by dt into r of t into sine of psi of t. Okay, so okay, so how do we define, means this r of t into sine of psi of t is nothing but the quadrature component. Okay, quadrature component of the noise. So that is what is told here. Okay, so nq of t will be equal to r of t into sine psi of t. So I can replace this by nq of t. I can say nd of t will be approximately equal to 1 by 2 pi AC d by dt of nq of t. So it is a quadrature component of the noise, right? Means the output of the discriminator will have a message component and as well as the noise component. That noise component will be having a derivative of the quadrature noise component. Okay, so already I said this, right? This additive noise, the nd of t, will be appearing at the output of the discriminator. Okay, discriminator is determined by the carrier amplitude because it is 1 by 2 pi AC, right? So the AC is the carrier amplitude, right? And as well as the quadrature component of the narrowband noise. Okay, so what is this one? This is the noise component at the discriminator output. So that will be determined by what? The carrier amplitude and as well as the quadrature component of the narrowband noise. Okay, so to find the output SNR, okay, so already we have defined, how do we define the output SNR? It is a ratio of average output signal power, right, to the average noise power. Right, means it is a ratio of what? Average output signal power or demodulated signal at the receiver output to the average noise output, average output noise power, right? So now with the previous equation means V of t, as I said, V of t, okay, here, this component, right? That is kf into m of t. So what will be the average uh, power of that signal? Similarly, then average power of the noise. I think we'll write it here only. Yeah. So what I wanted to say is the first term, right? The discriminant output will have this, right? Kf into m of t is there, right? So the average output signal power, I can write it as, see, m of t, I represent average power of m of t by a letter p, right? So it will be k squared into p. K squared into p is the average output signal power. Okay, and let us try to find out the average noise power also. Okay, to find the average noise power, so what we do is we write this in terms of frequency domain. This noise expression, this is the expression for noise, it is output of the discriminator, right? So we take Fourier transform and we write in frequency domain. So if I already, I think I said what is the Fourier transform of the derivative of a signal. So dy dt of x of t, that will be equal to j2 pi f into that, right? So I am doing that here. So if I substitute dy dt of something is nq of t will be equal to j2 pi f. Okay, and this term 1 by 2 pi ac is there. Okay, fine. So that is what I said here, j2 pi f. Fine. So j2 pi f is our the Fourier transform of this part, d by dt of nq of t will be what, j2 pi f, and the denominator term will be 2 pi ac. So 2 pi and this 2 pi will get cancelled, we will be getting jf by ac. Okay, that is what the noise component, what we can say. So what I can say is the power spectral density, okay, of the noise which is appearing at the output of the discriminator will be related to the power spectral density of the quadrature component of the noise. Okay, so I can write this the power spectral density of the noise which is appearing at the output of the discriminator will be equal to, as I said, the are related to the power spectral density of the quadrature component of the noise, right? So with that I can write see, we found what is the thing here, right? It is jf by ac, right? Jf by ac, this expression is for this nd of t, right? So with that, what I can say is, I can say yes, nd of f is the power spectral density of the noise, okay, at the discriminator, right? So which is equal to f squared by a square c into snq of f. Okay, where snq of f is the power spectral density of the quadrature noise component. Okay, snq of f is the power spectral density of the noise component, quadrature noise component. Okay, so with respect to that block diagram, as I said, the band pass filter, right? What we are using is an ideal band pass filter, right? Having a frequency response, right, with a bandwidth of dt and midband frequency fc, right? So that will be following the what, narrow band noise, right? So that will have a power spectral density characteristics similar to one which we have already discussed. I will show the diagram of that. Okay, so the quadrature component of the narrowband noise will have the ideal low pass characteristics. Okay, so with that, what I wanted to say is the power spectral density of that noise, that is nd of t, so which is appearing at the output of the discriminator, can be written as like this, that is s nd of f is equal to n naught. Okay, n naught is the value of power spectral density of the quadrature component of the noise. So remaining thing is fine. So f squared divided by a square c into n naught over this interval. Okay, when f is less than or equal to pt by 2, otherwise it will be 0. So just let me show the diagram of that. So this is the spectrum. Okay, power spectral density of the quadrature component of the narrowband noise, first term. So this exists over the interval minus bt by 2 to bt by 2. Oh, so this value is n naught. That is why in that expression we have written s nq of f as n naught. Okay, the rest of the term is written as it is. And see, when this is this s nd of f, no, s nd of f is the what, is the power spectral density of the noise at the discriminator, right? So the by diagram, see, power spectral density of the noise nd of t at the discriminator output. So as the frequency increases, it is increasing, right? So it will be like this. And when we pass this signal through a baseband low pass filter, right? See, output of the discriminator will be given to the baseband low pass filter. So the response of that will be this. So this is the output noise per spectral density, and which lies over the interval minus W to plus W, because the low pass filter bandwidth will be what? W hertz, right? So this is the power spectral density of the output noise, or it is the receiver output. Hope this is clear. These three diagrams. This is the power spectral density of the potential component of the noise, right? And this is the power spectral density of the noise which is appearing at the discriminator output, and this is the power spectral density of the output noise which is appearing at the output of the receiver. Okay, so with this, what I can say is, yeah, so output noise SNO of F will be N naught into F squared by A square over this interval. Only the frequency limits have been changed. Earlier it was BT by 2, now it is only W. Okay, otherwise it will be 0. Fine. So, because what we say, the low pass filter bandwidth will be what? From minus W to plus W hertz. With that, we say this. Okay, so the average output noise power, okay, will be determined by integrating this over the interval minus W to plus W. So that is what is done here. Okay, so average power of the output noise will be, so N naught by A square C is constant, we are taking it out. Then integral from minus W to W, F square into DF. So if you do the integration of this, okay, and if you substitute the limits, then you will be able to say what is the expression. Okay. Yes, quickly, is it possible to say F square into DF will be what? You will get F cube by 3, right? So the value of F will be, you are substituting upper limit minus lower limit. If you do that, and you will be this will be the expression. So this is the expression for average power of the output noise. Okay, now, so we found what is the output SNR, that is average power of the message signal at the receiver output, and we found what is the average power of the output noise. Then the ratio of those two will give you the output SNR. Okay, so I said out what is the average power of the message signal, that is equal to K squared F into P. Yeah, I think yes, I have done here, right? So K square F into P is the average power of the message signal, and we found what is the average noise power. So if you take the ratio of those two, you will get the expression for the output SNR. So output SNR, right, for the FM signal will be this. I hope we'll be able to understand this. Yes. Hello. Yes, you understood how we get this equation, output SNR. It is the ratio of what? Average power of the message signal, that is K squared F into P. Then, as I said, the average noise power will be what? 2N naught W cube divided by 3A square. Right? So if I substitute that, I will be getting this output SNR. So similar to that, we can find out what is the channel signal to noise ratio, right? So it is the ratio of what? Average power of the modulated signal, right? So which is equal to A square C by 2, and it is then average noise power, right, in a message bandwidth WN naught. So with that, I can write the channel signal to noise ratio for the FM signal will be A square C by 2 into WN naught. Okay. Then the ratio of these two will give you the expression for figure of merit. Okay, 6.4 divided by 6.41 will give you the expression for figure of merit. So which is done here. So this is the expression for figure of merit. So you just do and do the cancellation of the common terms. Okay, so what is common and all, then you will be able to see this equation. 3 into k squared f p by w square. I will stop with this. Let me continue in the next class.